So let's talk about where we've been. Okay, we're starting chapter 9. So in chapters 1 through 8, you studied descriptive statistics, probability, and inferential statistics. One of the techniques you learned in descriptive statistics and in Algebra 2 was graphing paired data with a scatter plot. Okay, so for instance, salaries and average attendance at home games for the teams in Major League Baseball. Okay, this is shown in the right as a graph and as a table right down here. Okay. Now, where are we going? In this chapter, we're going to study how to describe and test the significance of those relationships between those two variables when data are presented as ordered pairs. Okay? For instance, in the scatter plot above, it appears that the higher team salaries tend to correspond to higher average attendance, and lower team salaries tend to correspond to lower average attendance. This relationship is described by saying that the team salaries are positively correlated to the average attendance. Graphically, the relationship can be described by drawing a line called a regression line that fits the point as closely as possible, as shown below. This is the regression line that you can't see that I'm pointing to. This is the regression line right here. Okay? The second scatter plot shows below are the salaries and the wins for the teams in Major League Baseball in 2012. From this scatter plot, it appears there is no correlation between their salaries and their wins. Do you see the difference in these two? Yes? Okay, good. So let's talk specifically then. Let's talk about correlation and specifically. Okay, so first of all, an overview, which is general by definition, but whatever. Okay. Suppose a safety inspector wants to determine whether a relationship exists between the number of hours of training for an employee and the number of accidents involving that employee. Or suppose a psychologist wants to know whether a relationship exists between the number of hours a person sleeps each night and that person's reaction time. How would he or she determine if any relationship exists? Well, in this section, section 9.1, we're going to study how to describe what type of relationship or correlation exists between two quantitative variables and how to determine whether the correlation is significant. Okay, so first of all, a correlation is a relationship between two variables. Are two variables correlated? Do they have a relationship? This data can be represented by an ordered pair where x is the independent variable and y is the dependent variable. This book also calls the independent variable the explanatory variable and the dependent variable the response variable. Kind of makes sense though, doesn't it? Okay. So we learned that graphing ordered pairs is called a scatter plot, like these down here. Okay. The independent variable is measured on the horizontal axis and the dependent variable is measured on the vertical axis or the y-axis. Scatterplot can be used to determine whether a linear correlation exists between two variables. So this one, does that make sense that is a negative linear correlation? Because if we drew a line, what kind of slope would it have? Negative slope. What about a positive linear correlation? If I drew a line, what kind of slope would it have? Positive. These words are also important too. As x increases, y is decreasing. This one, as x increases, y is increasing. Okay? No correlation. Does it look like this data is correlated or related in any way? Not really. And what about this one? Is this data correlated? Yes, it is, but it is not a linear correlation, is it? That's not something we ever really talked about in Algebra 2, is it? We only dealt with positive and negative linear correlations or no correlation. But there is times when things can be correlated, but in a non-linear manner. You okay with that? Okay, so constructing a scatter plot. If I give you a bunch of ordered pairs, can you graph them? If I give you a bunch of ordered pairs, can you graph them? If I give you a bunch of ordered pairs, can you graph them? Yes, but here's the deal. Time is an issue for us, okay? I know that you know how to plot ordered pairs and graph them. Do we have time to plot 25 ordered pairs to graph them? No, we don't. So I need to make sure you remember how to do it in your calculator, okay? First thing we're going to do is turn our calculator on. That's a very important step, okay? We want to make a new document. So home, new document. No, I don't want to save my old one. and I want to make a list and spreadsheet document. Okay? So it literally looks like a spreadsheet, doesn't it? So I'm going to arrow up, right up here. What is my X variable called in this data right here? Duration, right? Now, I could put duration, or I could put dur, because I know that's going to stand for duration, or I could even put X, but I want to kind of maybe give it the name that it is here. I could totally type out the whole word duration, but I'm just going to go with dur because I think that's funny. Okay? Then right up here, what am I going to put here? Time. Okay, good. T-I-M-E. Probably not just going to put Tim because that would be weird. Okay, maybe you know someone to be named Tim. I don't want to offend them. Okay, now I'm going to go and just enter all my X values. Take a minute and enter all these X values. I made it real big so you can see it, but you probably can't see my calculator because of the glare. All I'm doing is entering my X values, all of the duration values into my X column. So you do the same thing, please, in your calculator. All right, sorry, I'll try to not block you. Okay, you got all the X's in? Okay, so here's what I did. I don't know if you saw me do it, but here's what I did. How many values should I have in my chart? How many X values? I should have 25, right? Well, I went and counted them to make sure I had 25. Now that's going to that added a couple extra seconds of time, but what it also saved me from was doing this all over again because I missed one. See what I'm saying? So take the couple extra seconds and go count and make sure that, or read the words. Sometimes the words in the word problem will tell you, well, there's 25 data points, and then I know. Okay? So time. Now go and enter all your Y values for time into your calculator. Okay, you got it done? Yes? All right, so here's the deal. I want you to notice my calculator list real quick. And if I go on to the next step without doing one thing right now, all of my work is going to be wrong. Can you tell me what that one thing that I need to do is right now? Yeah, I need to hit enter. Okay, I need to hit enter so that it enters that value. If I leave it there without hitting enter, all of my other stuff is going to be messed up, and I don't want that. Okay, so here's the deal. I want to go look at this. It's not necessary right now, but I'm just curious. Okay, so what I want to do is control doc to add a page. I want to add a page that is a data and statistics page. And if I was a betting woman, I would bet you that our graphs don't look the same right now. Okay? The calculators, for whatever reason, these never look the same. But we have to tell the calculator, no, calculator, this is X. That's the duration. That was the value I used for X. And then it moves all the dots. And then I have to go over here to the Y and click on that and say, no, calculator, that's the time. And then it gives me the graph. Okay, so go ahead and tell me right now what kind of, if any, correlation this has. Positive. Why? It's rising to the right, isn't it? Okay, if I drew a line, the slope would be a positive slope. Okay, so I actually want to go back to the other page because I was just curious about that. I want to go back to the other page. That's not necessary every time, I'm just telling you. Okay, because what I want is the equation of this regression line. I want all the information about it. Okay, so I want to go to my menu and I want to go to statistics and I want to go to stat calculations. What do I want? Don't I want my linear regression? So what's the problem? There's two of them. Which one do I want? Which one have I done since 7th grade? MX plus B, right? That's the one I want. Okay, so I want to choose number 3. So where is my X list? It's an A. So here's the weird thing, okay, that I will admit right now that I do not understand. Sometimes, those of you who program stuff, sometimes you have to have these little things in there and they don't mean anything, but if they're not there, then the whole program's wrong, right? So this is an A. Why are those brackets there? I don't know. Okay, where's my Y list? It's in B. Guess what I have to add? Those bracket things. They are right here. Control open parentheses. And when I add one, it adds both of them. Okay? Now, sometimes I might want it to save my regression equation. It's asking me where do you want to save it? Save it to F1. It doesn't matter right now. Okay? Frequency list, I don't have to worry about. Category list, I don't have to worry about. Including categories, I don't have to worry about. First, result column. Well, if A and B are where my lists are, I don't want to put my results in A or B. Now it comes up as C because it's read that I have them in A and B, so C is probably fine. Some people like to put it in starting in D so that there's a little space there, but it doesn't matter. Okay, I'm going to put mine in C, and then I'm going to hit OK. Okay, now my cursor was at the bottom of my list, so I can't see anything. If your cursor was at the top of your list, you might be able to see all this stuff already, but I'm going to up arrow a little bit so I can see some stuff right now. Okay, so first of all, it's saying this is linear regression. That's the title. Regression equation that they used was MX plus B. Well, here's M and here's B. So I could go write out my equation right now. 12.4809x plus 33.6829. That would be my linear equation, right? Any questions about that? You remember how to do linear regression. Put this in X and Y in a stat list and spreadsheet, excuse me, and then use those keystrokes I just showed you to find the equation of the linear regression. Okay? The first 3 examples talk about finding the equation. We're not going to do it by hand. We're just going to use the calculator for time purposes. Okay? Because you know how to do it by hand if I needed you to. Okay? Then there's this beautiful, beautiful formula for finding the correlation coefficient. This is not something that we did in Algebra 2. It wasn't necessary. It's not on my list of stuff that we need to talk about. But we need to talk about it now. Okay? Look at this beautiful formula. Does it even make any sense to you? Take the number of terms, multiply it by the sum of the x times the y, subtract the sum of the x's times the sum of the y's, divide all that by the square root of the number times the sum of the x squareds, minus the sum of the x's squared, times the square root of the number of terms times the sum of the y squareds, minus the sum of the y's squared. Hey, look at that. R. Hey, look at that. R. Isn't that nice? I'm going to give you this formula on your formula chart like I told you I would. We probably won't use it. Okay? What I need you to be very clear about, though, is the correlation coefficient, which I've really been unable to say today, so if I mess it up later on, just please forgive me. Okay? It measures the strength and the direction of a linear relationship between two variables. The symbol R represents the sample correlation coefficient. The formula for R is that beautiful formula, and it is the sample correlation coefficient. If there's a sample correlation coefficient, guess what there also is? Population correlation coefficient. Okay? It is represented by this, which is the lowercase rho. It's a Greek letter rho. Got it? Okay. So the range of correlation coefficients is between -1 and +1 inclusive. Your correlation coefficient could be -1. It could be +1. It could be anything in between. When x and y have a strong positive linear correlation, R is very close to 1. When x and y have a strong negative linear correlation, R is very close to -1. X and y could have a perfect positive or a perfect negative correlation, which would be your R would be a 1 or a -1. If it's perfect positive, it's 1. If it's perfect negative, it's -1. Okay? When there's no correlation, no linear correlation that is, then the R is close to 0. So the closer it is to the ends, the ones, negative or positive, the stronger of a either positive or negative correlation you have. The closer that R is to 0, the less correlation it has at all. Okay? So it's important to remember that when R is close to 0, it does not mean that there's no relationship between x and y. It's that there's no linear relationship. Does that make sense? Okay? Because based on that first example that I showed you right up here, there could be a correlation. It's just not linear. Remember this one? Okay? So let me show you a couple examples that they give you that I can give you right now. Let me zoom out a little bit, not in, out. So here's one example. The number of adult movie tickets versus the total cost. Well, that's perfect positive correlation because it's going to increase by the same amount every single time, right? That is a line. Does that make sense? Height in inches versus shoe size. Does it make sense that the taller you are, the bigger your shoes would be? Yeah, so that's a strong positive correlation, but it's not perfect because not everybody increases their shoe size exactly the same amount by how tall they are, right? But it is a strong positive correlation. Then there's a weak positive correlation, which is income per year versus the amounts you spend on milk. To me, that's almost no correlation, but whatever. They say it's weak positive, so we're going to go with weak positive because they did the math, and this is close to what? 0, but it's still a positive number, so that's a weak positive. Does that make sense? Okay. Here's another one. Perfect negative correlation. The number incorrect based on, relating to your exam score. That seems pretty obvious that it would be a negative correlation, right? The more you miss, the less your score is. Okay. Strong negative correlation would be the number of absences versus your test grade. The more absences you have, the lower your test is going to be. Now, it's not a perfect one because there's some of you guys that are that can still know how to do stuff even when you're absent, right? Okay? But chances are the more you miss, the lower your test grade is going to be, right? No correlation would be your IQ score versus your height. I know some of you disagree with that, but statistically, there's no correlation. Okay? There are some guidelines for using this beautiful formula. Do you need to talk about them? No? Okay, good. Then it talks about calculating your correlation coefficient. Again, that's something we're going to use our calculator for. Okay? Then it talks about using a table to test a population coefficient of P, or what do we really call it? Rho, right? The lowercase Greek letter of rho. Once you have calculated R, which is your sample correlation coefficient, you're going to want to determine whether there's enough evidence to decide that the population correlation coefficient rho is significant. In other words, based on a few pairs of data, can you make an inference about the population of all such data pairs? Remember that you are using sample data to make a decision about a population, so it's always possible that your inference may be wrong. In correlation studies, the small percentage of times when you decide that the correlation is significant when it's really not is called the level of significance. Now, have we dealt with level of significance before? Yes, so it's not something that you're completely unfamiliar with, right? Okay, so it's typical to set that level of significance at 0.01 or 0.05, so 1% or 5%. Okay? When it's at 5%, you'll probably decide that the population correlation coefficient is significant when it's really not 5% of the time. Or if we're doing the 1%, it's really not 1% of the time. Okay? When using a lower level of significance, you may fail to identify some significant correlations. You might. Okay? In order for a correlation coefficient to be significant, its absolute value must be close to 1. So to determine whether the population correlation coefficient rho is significant, we're going to use our critical values in Table 11 of Appendix B. Now, some people were confused earlier and thought, oh yeah, this is what we use for level of significance, so we'll just use that again. Okay? Please notice this is Table 5, and they're telling us to use Table 11. So let me show you Table 11 real quick, and you'll very quickly realize it is not the same table. Okay? Table 11 is right here. It looks similar, but there's nothing about tails in it, is there? Well, here's why. Okay? First of all, we figure out what our number is, and then we figure out if we're using 5% or 1%, and we just go read that number. It's not a hard table to read. Okay? But here's the deal. That deal is in a second. Hold on, I'll tell you that deal in a second. Number of pairs, how many sample pairs are there in the data? If we're using 1%, we look over here, 0.959. So here's what we have to look at to decide the significance. If the absolute value of our R, what we found using our calculator, is greater than the value from the table, then the correlation is significant. Does everybody understand that? Figure out what our R is. So let's look at this R. Our R is 0.978659 in this particular example that we just did. And there were 25 examples, right? 25 samples, excuse me. If we're trying to decide if this problem that we did just a second ago, if it is significant or not, I would have to turn to this table. Table number 11, table number 11, and I would have to look at 25, and I would come over here to either 5% or 1%, depending on what it's asking me. Okay, let's just say 5% for now. That's 0.396. Everybody, can you remember that for just a second? 0.396 is the absolute value of our R greater than 0.396. Yes, so we're saying then the correlation is significant in this particular example. Okay? Otherwise, if it's not greater than that number, then there's not enough evidence to conclude that the correlation is significant. So that's just saying if it asks you, decide if it's significant or not. and go with that. Okay? So there's some guidelines to remind you how to use table 11. Okay? There's an example of reusing it. I just showed you one, so we don't really need to talk about that. Here's what I was thinking of a second ago. Remember in hypothesis testing how much fun we had doing hypothesis testing? Nobody remembers the fun? Do you remember doing hypothesis testing? Oh, yes. Okay. So hypothesis testing for population correlation coefficient. Remember we had our null hypothesis and our alternative hypothesis, and our null always had to do with where the equal sign was, and then our alternative hypothesis was just the other one besides what the null was, depending on where our claim was and all that sort of stuff. You remember doing all that, right? Here's the thing. In this text and all the problems that we're going to do right now, we're only going to consider two-tailed hypothesis tests for row. We only have to do two-tailed. So we're only going to be doing either equal or not equal. Does that make sense? That helps because in a minute, or right now, we're going to talk about a t-test for a correlation coefficient. Okay? And in a t-test, we do use this chart. We do have to know levels of confidence. We do have to know degrees of freedom. But we only have to look at two tails. That helps, right? Helps us know where to look. Okay? So the thing about it is, here's this beautiful formula for finding the test statistic. Well, the test statistic is the R, and the standardized test statistic is our T. And here's this beautiful formula. It's just the R divided by the standard deviation of that R's, and here it is all written out for us. Okay? Now, why is the degree of freedom n minus 2 this time? Any guesses? Two-tailed? Another guess earlier was because there's an X and a Y. We're dealing with two kinds of information. Okay? I just know that it's n minus 2. Fair? Okay? So we are going to use our degrees of freedom. So if we're looking at our 25, we're looking over here and saying, well, that's 23, right? Okay? Take you through the guidelines right here. You've got to know your null hypothesis and your alternative hypothesis. You want to identify your level of significance. It'll tell you, right, what you want to use, 1% or 5%, or even other stuff, but mostly it's 1% or 5%. Okay? Find our degree of freedom. So however many terms that we have, we subtract 2 to find our degree of freedom. Use the table 5 in Appendix B, which is this one, our T table or T distribution table. Okay, to figure out what our number is. So 23, and if we're going on 1%, that would be 2.807. Not a difficult table to read. We've read it before. And then we want to make a decision to reject or fail to reject based on the hypothesis, based on the claim, things like that. Okay. One more thing to show you very quickly is 9.2. 9.2, you got to know what a regression line is. You already know, don't you? We dealt with it in Algebra 2. You know what a regression line is. Okay? There's this beautiful formula right over here for finding M. If we're finding a regression line, we don't have to worry about that because we're letting our calculator find our regression line for us. And that's the end of that section. Okay? Any questions? Okay, we'll work on this week. Ask questions as we go, all right? Peace.